Hello, my name is Michaela Williams and I am a biomedical engineering major from the class of 2019.
And my name is Kalina Gardiner and I'm a nutrition major from the class of 2018. We will begin working through problem number 33, chapter 6, on page 41 in the general chemistry workbook. You should begin by working on the problem by yourself to see if you can get the answer. Pause the video now until you have completed the problem. Then we'll go over it together.
The problem is the photoelectric work function of a metal is the minimum energy needed to eject an electron by irradiating the metal with light. For calcium, this work function equals 4.34 times 10 to the negative 19th joules. Part A asks, what is the minimum frequency of light required to observe the photoelectric effect? For this part, we will use the Planck-Einstein relation E equals h nu. In this equation, E is the energy measured in joules, h is Planck's constant, and nu is the frequency measured in hertz. If we rearrange the equation to solve for the unknown, we get that nu equals E divided by Planck's constant. Since the frequency and energy are directly proportional, the minimum energy will be used to find the minimum frequency. Since the work function is the minimum energy required to eject an electron, we will plug in this value for E. Also, Planck's constant is 6.626 times 10 to the negative 34th joules seconds. So if we plug this into the equation, we get that the frequency equals 4.34 times 10 to the negative 19th joules divided by 6.626 times 10 to the negative 34th joules seconds. And if you plug this into your calculator, you get that the answer is 6.55 times 10 to the 14th inverse seconds, also known as hertz. And for this answer, we only have 3 significant figures because the only information given in the problem is the work function, which is also 3 significant figures.
Now on to part B, which asks if light with a wavelength of 256 nanometers impinges on a piece of calcium, what is the speed of the ejected electron in meters per second? For this part, we will use the photoelectric equation. Kinetic energy equals the energy of a photon minus the work function. Kinetic energy equals 1/2 mv squared. M is the mass of an electron measured in kilograms, which equals 9.11 times 10 to the negative 31st kilograms. V is the speed of the electron, what we are finding, measured in meters per second. The tricky part of this equation is knowing the mass we want is of the electron and not the mass of the metal. We use the mass of the electron because we want the mass of the thing that is moving. The energy of the photon equals hc over lambda. In this equation, h is Planck's constant, 6.626 times 10 to the negative 34th joules times second. C is the speed of light, 3.00 times 10 to the 8th meters per second. Lambda is the wavelength measured in meters, which is given. So in order to solve for the speed of the electron, we rearrange the equation to V equals the square root of hc over lambda minus the work function. All of this times 2 over m. We now can plug and chug. So now that we have plugged in our values into the equation, we can punch them into our calculator and we get that the speed of the ejected electron equals 8.67 times 10 to the 5th meters per second. And that's our final answer.
Now on to part C, which asks, if light with a wavelength of 345 nanometers impinges on a piece of calcium, what is the speed of the ejected electron in meters per second? Part C is very similar to part B, the only difference being the wavelength. So in order to solve this equation, we will be using the photoelectric equation rearranged like we did in the last one. So we have that the speed of an electron equals the square root of Planck's constant times the speed of light divided by lambda minus the work function times 2 over the mass of an electron. So now that we have the equation, all we have to do is plug in all the known values to get the speed of the electron. As you can see, I plugged in all of the known variables and converted the wavelength from nanometers into meters. So now, plugging in this entire equation into your calculator, we find that the speed of an ejected electron is equal to 5.59 times 10 to the 5th meters per second.
That finishes problem number 33 from chapter 6 on page 41 in the general chemistry workbook. Thanks for watching.